Hello everyone, this is QB in the Group episode 4, and today we are going to look at the parity of permutations. For those who are new to this word, parity means whether a number is even or odd, or in other words, divisible by 2. And before we start, let's review some basic concepts in the last video. Transposition. A transposition is a special kind of permutation and only switches two elements in a set. For example, bracket 1, 2 is a transposition and bracket 1 to 3 is not. However, we can write bracket 1 to 3 into the products of transpositions as bracket 1, 2, bracket 2, 3, and we can do similar things on bracket 1 to 3, 4. But why do we care about parity? I'm going to pose a question that puzzles me for years when I first started playing the Rubik's Cube. Look at this cube on the screen. Can we switch the opposite cubies without breaking the cube and reinstalling each cubie? I tried several times and Nether just told me, "Hey Scott, this is not on the PLL formula list." And speaking of PLL, it's one of the steps in the CFOP cube solving process, and it basically puts all the cubies in the highest layer into the right positions just by one formula for each case. But anyway, I cannot find certain movements of the layer to accomplish this clever switch. This video will tell you the answer and actually prove it. Now let's get back to some abstract concepts about permutations. First, can every permutation be a product of transpositions? The answer is yes, and the idea is very simple. Every time you switch two elements out of n elements, you put one element in its right position and deal with the other n-1 elements. The formula is given on the screen. If you now look at the permutation bracket A1, A2, A3, all the way to an, it can be also written as the product of n-1 transpositions. This inspires mathematicians to define the parity of permutation. An odd permutation is the product of an odd number of transpositions, whereas an even permutation is the product of an even number of transpositions. However, we should be very cautious. Can some permutation be both odd and even? In other words, is there an intersection between the set of odd permutations and the set of odd even permutations? If so, then the definition is somewhat unsatisfying because people always want things to be either black or white, but not in between. The answer is no, and we will introduce the parity theorem of permutation to prove this property of permutations. First, let's suppose that for a permutation sigma, there are two representations by transpositions. The first one is tal of 1, tal of 2, all the way down to tal of A, and the second one is tal of 1 prime, tal of 2 prime, all the way down to tal of B prime. In order to prove that a permutation is either even or odd, we have to prove that A equals to B under mod 2, or A and B has the same parity. But now, to make the permutation sigma less special, we find out that the inverse of sigma equals to tal of A minus 1 all the way down to tal of 1. And multiplying sigma and the inverse of sigma gets the identity E equals to tal of 1 prime, tal of 2 prime all the way down to tal of B prime. Then multiplying tal of A minus 1 all the way down to tal of 1. So this will come to a question. Now we only have to prove that the identity permutation E can only be a product of an even number of transpositions, because then it would imply that A and B must be equal under modulo 2. So next we want to use a trick similar to mathematical induction. It suffices to prove that if E is the product of n transpositions where n is larger than 2, then it's also the product of n minus 2 transpositions. If we can prove that this is true, then if E is an odd permutation, then E itself will be a transposition, which is absolutely wrong. Let's see how we rewrite n permutations into n minus 2 permutations. Suppose that E equals to tal of 1, tal of 2, all the way down to tal of n, where all the tals are odd transpositions. And then we consider a particular transposition, tal of k, equals to bracket xy, and its neighbor, tal of k minus 1, and then we consider 4 cases of tal of k minus 1. So first, if tal of k minus 1 equals to tal of k, then tal of k minus 1 times tal of k will be the identity element E, because you just switch two elements and switch them back. If we delete these two transpositions from the above product, the result will not change, but the total number of transpositions will reduce to n minus 2. And second, if tal of k minus 1 is unrelated to x and y, namely bracket zw, then we can simply switch the tau of k minus 1 and tau of k, and the result doesn't change. And the next cases are more complicated and require more skills. If tau of k minus 1 equals to bracket xz, which is related to x but not y, then we can switch tau of k by noticing that bracket xz times bracket xy equals to bracket xy times bracket yz, and yz is unrelated to x. To check why it's true, you can compute the product yourself on the draft paper or look at the hint on the screen. The last case is similar. If tau of k minus 1 equal to bracket yz, then there is bracket yz bracket xy equals to bracket xz times bracket yz. And now bracket xz is not tau of k anymore, but it's related to x. So we then denote bracket xz as tau of k prime. Now let's look at the summary of the whole process. We try to make terms that contain x forward. So we can choose k, such that tau of k is the last transposition containing x. And during the process, we move tau of k forward or change that to tau of k prime. If we encounter case 1, which is tau of k minus 1 equals to tau of k, then we're done because n is reduced to n minus 2. Or we finally move tau of k or tau of k prime to the first transposition, and then the other transpositions are all unrelated to x. However, now we switched the element x but didn't switch it back, so this permutation cannot be the identity E. So this is a contradiction that proves the theorem, because for any permutation that can be written as n transposition, we can reduce the index n into n minus 2. And therefore, we have proved that if E is the product of n transpositions, then it's the product of n minus 2 transpositions. And therefore, following our previous logic, E must be the product of an even number of transpositions, and thus a permutation cannot be both even and odd. This gives us a perfect partition of all the permutations into the odd ones and the even ones. But why that matters to the previous question is because we can look at a parity of permutations on a cube. For example, for our old friend R permutation. Do you think R is an even permutation or an odd permutation? What is the parity of R? Review that by considering the corner cubies and edge cubies. R equals to bracket 1, 2, 3, 4, bracket 5, 6, 7, 8. Then we can easily write these two permutations into transpositions, and there are 6 transpositions in total. Hence, R is an even permutation. Similarly, all other basic operations on a cube are even permutations. This makes us conclude no matter we do anything on a cube, we are doing an even permutations to the cubies. The above result implies that if we are given an odd permutations on the cube, we cannot make it happen without reinstalling the cube. And for our original question, can the opposite cubies switch their positions? We can first denote these cubies as x and y, and since xy itself is an odd permutation, there are not any possible permutations on the cube that make this possible. Although we've partitioned all the permutations into odd and even ones, how many of them are odd and how many of them are even? And further, does odd, or even permutations form a group structure? Actually, there is a special group called alternating groups, which is related to the even permutations upon a set, and we will dig more into that in our next videos. And thank you for watching Cubing in a Group. In the next video, we will introduce a very fundamental concept in the group theory, the subgroup. And please feel free to subscribe to my channel or leave your comments below. See you next time.